Okay. Good morning, good evening, all the Digital Futures world. It's a great honor for me. This is Philip Yuan from Tongji University, Shanghai. So tonight and this time we have a special keynote, Digital Futures keynote talks. We invited two very important speakers, Martin himself and Fabian Schurer. Tonight, the topic is material agency in wood architecture and BIM to fabrication. So I want to firstly briefly introduce the two speakers. Martin himself is the founding director of UK-based timber design to construction firm, Xylotek, and head of AA Design and Make Master Program. Martin himself is engineer, geometer, and educator who has specialized in innovative timber structures since 2005. Following the background of aerospace engineering, he was founder member of Arab Advanced Geometry Unit from 2000 to 2006 and director of Hooke Park from 2010 to 2018. The AA Woodland campus for experimental timber architecture. Key previous projects include 2005 Serpentine Pavilion, for which he developed in the pioneer application of geometric scripting for robotic fabrication. The form finding for the Pompidou mass timber roof as its concept design stage, tutoring the AA's Summer Pavilion from 2006 to 2009, and directing the design and construction of series of timber buildings at Hooke Park that radically explore the use of local ground wood. And the second speaker is Fabian Schurer. Fabian Schurer is co-founder of Design to Production and leads the company's office in Zurich. He graduated from the Technical University of Munich with diploma in computer science and architecture, and gathered professional experience as CAD trainer, software developer, and new media consultant. In 2002, he joined CAD Group at ETH Zurich, where he co-founded Design to Production as research group to explore the connections between the digital design and fabrication. In 2007, Design to Production teams up with architect Arnold Watts and became the commercial consulting practice and supporting architects, engineers, and fabricators in the digital perfection of complex design. Over the past decades, Design to Production has gained great reputation for planning non-standard timber structures like the Centre Pompidou in Mass and the Swatch headquarters in Bale, both designed by Shigura Ban, and the new Cambridge Mosque by Marks Butfield. Recently, they have started to look at more standard buildings and how to develop a new digital process for pre-fab timber structures. So I want to make a very brief background introduction for today's topic. Building construction is currently responsible for roughly 30 to 50% of global energy consumption, waste production, and greenhouse gas emissions. Construction volume is still increasing rapidly in order to house a rapidly global population. However, skilled and unskilled construction labor in the short supply, especially in developed countries. The program we're facing now is to build higher volumes with less labor in a way that is friendly to the environment and to our planet. Timber construction has been increasingly regarded as the most sustainable and promising solution to address the great ecological changes facing the construction industry. Building with wood could store carbon for long, as timber products lock approximately 1 ton of carbon dioxide per 1 cubic meter of wood. Construction industry can make a real difference by using wooden materials that both capture carbon for their entire lifespan, as well as produced with little carbon dioxide emissions during production. Timber construction also enables high level of prefabrication and automation. Short construction times making the timber construction one of the most digitally advanced within the construction field. Timber construction is undergoing an increasing growth in recent years for its unique characteristics. Challenges such as the unreliability of natural-grown wood was mostly overcome during the last decade through material technologies. Not only the exotropical properties are increasingly being viewed as driving factors in timber construction, but also engineered wood products with more homogeneous properties have made timber one of the most lightweight building material with extraordinary strengths. Engineered wood products such as LVL-CLT continues to promote innovation and wider application of wood structure buildings. Wood is increasingly have become a new favorite in spatial structures, multi-story buildings, and rural construction. Due to the changes in building standards that allow the use of timber structure in different kinds of building types, especially multi-story and high-rise building. The last decades, we have witnessed the explosive growth in timber construction worldwide. As wood is still a valuable source, it is ideally used with maximum of efficiency in construction to minimize material costs. High quality, material efficient construction implies increased manufacturing complexity that can only be achieved with advanced construction technology, such as computational design, image-based quality control, CT scanning, CNC manufacturing, and robotic fabrication as well. In the context, we developed the robotic fabrication technology for timber construction during the last 2 decades, have attached a lot of focus and also achieved remarkable achievements. Relevantly, studies have been conducted a large range of research institutions like AA School, ICD, ETH, EPFL, and Tongji as well. Different robotic technologies have been developed in the construction of different timber materials, from logs to all kinds of engineered wood, like glulam and plywood walls. The researchers show a wide range of concerns, including the subtractive fabrication of individual building elements, additive assembly into prefabricated buildings modules, that is robotic placement and drawings, and also adaptive fabrication and quality assurance. So compared with convenient construction methods, the primary cost can be somewhat higher, especially for complex and wood structures, which are largely due to the dependence on the digital technology. But at the same time, the development of digital technology has not yet been fully developed. The wood construction industry needs not only automation, but also flexibility and adaptability that able to meet customized, costly changes requirements from different projects. So today it's a great honor to invite the both expertise specialist, Martin and Fabian. I think the 2 lecturers will greatly highlight the background, what I introduced. So firstly, I think I want to give the screen to Martin. And Martin, I think I will quit the, would you please share a screen and start your lecture? So Martin, please.
Great. Thank you, Philip. Thank you for the invitation. Setting of the context there with just an explanation of the current status of, I guess, the timber construction industry and the sort of role of emerging technologies within that. I titled this little talk Material Agency in Wood Architecture. I'll explain that a bit more in a second. I'm going to talk from 2 perspectives. My life is sort of split between 2 things. I'm the director of Xylotek, which is a startup timber design construction firm, which I guess has a sort of set of ambitions, but obviously has to operate in a kind of commercial context. So I'll talk about some of those projects which are I suppose, sort of deploying ideas and technologies, design technologies, and a sort of real drive through making, but within sort of the reality of commercial projects. Then I'll talk about Hooke Park, which is the Architectural Association's woodland campus. It's a remarkable place, situated in the woodland. Students design and make hands-on in the workshop using wood, trees from the surrounding woods. So it allows a very sort of, I guess, particular and kind of intimate relationship between the forestry and the production of timber architecture. So I'll weave a bit between those two worlds and try and sort of illuminate some ideas. So material agency. I think these quotes from Manuel Delanda are quite helpful. I'm just going to read them out. So historically, he's saying craftsmen did not impose a shape, but rather teased it out a form from the material. Instead of imposing a sellable form on an inert matter, materials were allowed to have their say in the final form produced. Design in which materials are active participants in the genesis of form. So I think we underline this talk is some of those ideas, I guess, particularly in the last one. The material, in this case, what we're talking about, wood, being an active participant in the creation of form. Not just some sort of material stuff that gets manipulated, by hands or machines, but a material where the material so the material characteristics itself inform the process. So if we talk about wood, as an active participant in this kind of material agency, we have to think very carefully about what wood actually is. It's a complex material. It grows itself. It's vascular. It's basically a transport system as well as a structural system. It's stochastic. There's a lot of randomness and variation within it, and it's non-isotropic. Anisotropic. It varies very much in different directions within its form. A conventional piece of wood, that's a linear sort of arrangement, but in other bits of the tree, you get much more complex geometric relationships and very different behaviors in different directions. Wood's an exceptional, incredible material. It has a very, very rich history. It's possibly our species' first construction material. This is a photo looking up the spire of Salisbury Cathedral, 115 metre high spire, which, the stone spire is supported by this internal scaffold. A 12th century piece of construction. You can kind of see it's obviously hand hewn. It's working very sort of inventively with the natural forms of the materials. And remarkably, when we had a tour of this with students about a year ago, I suppose, they're actually explaining that a lot of this wood is actually being reused from the previous wooden construction. You can actually see relics of connections that were used in a previous use. So I guess just to kind of capture the longevity and the potential as a structural material, building to such a huge height, in medieval times. More contemporary, I suppose, a reminder of the sort of the high performance capacity of wood. Until last year, the biggest wingspan aircraft that had flown was Howard Hughes's H4, the Spruce Goose Hercules aircraft, entirely built out of plywood. You think of aircraft needing to be sort of aluminium or some kind of advanced alloy, but there's the capability of wood is remarkable. The tree itself, I guess, as a sort of analogy for what we would ideally want from architecture, is worth thinking about. This is quite a long list of kind of characteristics it has. I mean, if you could achieve just a handful of these in a building, would be celebrating. I think there's maybe a couple of them to pick out. I mean, the fact that the tree adapts to its loading condition and its structure, optimizes its own form to capture energy, builds its own communication systems, as we're only really just starting to discover. It has a life of hundreds of years, and really it kind of boils down to it's an autonomous 3D printer of structural material that we can use. Not only is it that, it's a 3D printer that's making material out of atmospheric carbon predominantly. I guess the carbon argument, Philip introduced it nicely. You know, I think if as a species we're going to satisfy our ongoing need for shelter and our need to, you know, reach net zero CO2 emissions, it's totally clear, like we can't keep using cement and steel. You know, 11% of CO2 emissions, you know, sort of coming from construction building materials. I think even if you look at, given that part of sort of the industrial use as well as also steel and cement, you know, there's a you know, a massive need to push timber construction. You know, the IPCC, you know, the climate change body, you know, they're stating it. You know, wood products can displace more fossil fuel intensive construction materials, resulting in significant emissions of reductions. Kind of interestingly, and as a little bit of a sort of possibly a warning or something to be aware of. Sorry, I missed a page there, didn't I? Hold on. So I wasn't showing you the graph, but I think you're probably most of the audience are familiar with the pie chart. Obviously, the relevance of construction in global CO2. Yes, that top quote from the IPCC basically stating yes that we do need to shift to wood products. I guess the bottom one is a sort of flag, I suppose, that needs to be done with a deep consideration of, you know, the forest management, but also, I guess, forestry as a kind of global energy system. You know, that we have to think very carefully if we're really going to be serious about wood becoming such a prime material, that we also need to think very, very carefully about what that means at a forestry level, how we kind of maintain diversity and, you know, ecological systems and the kind of the richness that forestry needs, that it doesn't just become a kind of industrial factory for a kind of monoculture of timber production. Yeah, I'm sort of hinting at things I'll talk about later when we talk about how we actually work with diversity of forestry later. This diagram on the left by Mantau is a amazing capturing of the flow of wood material in Europe. I think because of produced in 2011, so probably adjusted a little bit, but I guess gives a sense of the complexity of the sort of the material flow from forests, some of the cycles that happen within forestry in itself, and there's various routes of wood products entering you know, sort of different industries, and then where they end up, I suppose. And I think as architects, you know, as engineers or whatever, we need to be very conscious of that that sort of end state of our wood. You know, okay, we grow the trees, they become parts of buildings. That's great, the carbon sequestered for, you know, a lifetime, 50 years, 100 years. But at some point that wood is going to have to go somewhere else. So I think, you know, a consideration from the outset, you know, these things are linked, it is ultimately a cycle. You know, I guess it's only the ones at the right hand end of this diagram that are actually not putting carbon ultimately back into the atmosphere. You know, so whether it's sort of recycling by breaking the material down and reusing it in some form, or a direct reuse of the material, you know, without sort of having to kind of, you know, break it down into pulp, whatever, or strategies of like burying the wood in a way that doesn't then decay and produce CO2 through its decay. So I think there's some, you know, interesting work to be done around how, you know, how this all gets acknowledged, and I guess really how we think very carefully about what we are doing to our wood in putting it in buildings. Like gluing it up in, you know, in lamination is great as a kind of way of making the material consistent, but it has this penalty. We're basically making a wood plastic composite, you know, which is ultimately going to be problematic, quite possibly for its ultimate reuse, or you know, if we are looking at strategies of burying it back in the ground. Okay, so sort of some hints possibly about how we think carefully about how we're using wood, and possibly a hint that kind of argument I'll come to later on, but that you know, that there are ways of thinking about using wood where we're taking its inherent positive characteristics, its diversity, and using that sort of directly, beneficially, rather than trying to average those characteristics out. Okay, just picking out another one of this long list of things that the tree does. The fact that it creates its structure in response to loading, to me, as someone with an engineering history, is really interesting. That there is a optimization process going on through the growth mechanisms. The way that the cells are created and the cambium of the wood is being directly influenced by the forces that the tree is seeing, the tensions, compressions, which way the wind's blowing, what forces the branches are having to take. It's a highly evolved, highly sophisticated, almost kind of topologically inconceivable process. If you think about how a branch and a trunk actually gets integrated and how the growth layers get laid on top of each other. So there's a real richness there. I think that Pannoni's sculptures, where he's exposing what a tree actually is, which is this layering up of all the previous annual trees, is really kind of thought-provoking. That this tree isn't just a kind of a lump of wood. It is a kind of a capturing of its own history, layer by layer. And things that we think of as a flaw in wood, as a problem, like the knot, it's a weakness, it's it's a defect, it's something that in glue laminating or CLT or one of those kind of engineered wood strategies, the process is one of basically sort of averaging out what these apparent defects, giving them less of a role in the structure. But there is an alternative way of thinking about it. Obviously, that strategy makes a lot of sense. There is value in that kind of process. But on the other hand, like the tree, like these things aren't a defect from the tree's perspective. They are a structural connection. They are the way in which the branch has been integrated with the trunk in a structural way. So there's kind of a prompt there, I suppose, to really sort of think through sort of anatomically and kind of topologically, what sophistication has the tree got already, and are the smart things that we can do to use that. Okay, so I think, just to sort of remind, I'm going to come back to these quotes a couple of times, but again, if we allow the material to have a say in the final form, what does that mean? And that can happen at various levels, whether it's sort of directly using these features we're talking about, or more just a kind of understanding what elasticity and plasticity does the wood have? What does it want to do? What doesn't it want to do if we're going to sort of deform it and place it in a certain way in a structure? Okay, I'm going to talk a little bit about Xylotek. This is a startup timber construction firm, UK based, with sort of also bases in France and Germany. Three of us set this up a couple of years ago. We'd met actually at Hooke Park, so we've been involved in projects there. Charlie Brentnell's, I guess, largely responsible for the renaissance of timber framing in the UK. So back in the 1980s, set up a firm called Carpenter Oak and Woodland, which went on to really sort of create a rebirth and understanding about traditional timber framing, and has moved that into a real sort of richness of understanding of timber structures. Oscar has a background also in very rich background and experience in timber, works a lot on sites and industry. He's now the managing director of Xylotek, driving it forward. We're a team of 12 now, so we have a sort of a mix of people, both kind of designer side and maker side, and some crossover between those. We sort of bring a history of projects from our different worlds and experience into that. And perhaps just something to sort of talk about a little bit. So I think we all share this premise, I guess, that to really understand wood, it's good if you've actually worked with it, if you've spent time with it, if you've understood it hands-on, and if you've had a kind of embodied phenomenal relationship with the material. You understand what it does, what it weighs, how it cuts, how you shave it. You really get to understand it sort of intuitively, what its structure is. Now, I think we talk about it, with the students, that the thinking does depend on a body, and in a way, intelligence. The idea of a sort of situated intelligence, where your physical interaction with the world is really fundamental, I guess, sort of runs through, in a way, what motivates a lot of us, that we really want to be combining a kind of material understanding and a design ambition. There's Charlie on the left, probably some point in the 80s working on the rebuild of a traditional wooden barn. This is Oscar building his own house, a very, very skilled carpenter and maker in timber. Charlie's experience includes quite a lot of restoration work. This was a big trestle bridge in Vancouver Island. He also has an experience with the company he set up, still running, Emmanuel Henry, where they did some really, really beautiful, precise work. This is a facade in oak. And the broader team, so again, as sort of members of this team also have bits of hands-on experience. So Fluji was part of the Hello Wood, the Hungarian design build sort of academic and workshop company. So it has a great sort of tactile feel for material. Jack Draper is one of our project managers. Jack's a very kind of skilled furniture maker. He's been making these beautiful chairs, as well as understanding construction at a larger scale. Tom Dawson, covered in sawdust. He sent me this image this morning, and I had to share the file name of the photo. I think it was just such a nice description of what's going on. But he has a background. He trained in France, where there's a great tradition of traditional carpentry. He worked as a carpenter. He understands very intimately what it means to work with wood. He is also a skilled digital designer, and works on the project management and design side. And I guess the point really is that we are trying to really merge the worlds of the making and the designing and kind of link those things together. We're working sort of across projects from inception to their final delivery. We're keen to be involved early on in projects, to work closely with the architecture and with the architect and engineer, see them through the fabrication to the completion. I think that idea of being involved early in a project is valuable, because it gives an opportunity to really sort of inform a project well by an understanding of wood. Like I said, we've sort of got sites in various places and a workshop base where we can do sort of small to medium-sized stuff. I'll skip over this slide probably, but just I guess just a sort of a premise for us as a UK firm. Obviously, there's to some degree of uncertainty still, some horrific consequence of Brexit to come. But I think it's interesting. The UK is home to a very large architectural engineering community. It has an underdeveloped timber industry, construction industry. So a sort of close relationship with the Central European fabricators and consultants like design to production. I think there's those links to be forged, and sort of something interesting in how the relationship with the European timber industry can relate to the UK. Okay, enough sort of spiel about the company. I'll show a couple of projects just to kind of give a sense. So I think as a firm, this was one of the first things we realised. A nice little roaming theatre project. So in Larch, it was Glulam Arch. The idea of this was that it could be a sort of public event for its erection. So after this stage, there's then so the sort of pop-up strategy, and the community can get involved, particularly in this last stage. You'll see in a second as a lifting of the central dome through a series of winches. The roof locks up, and a big sort of canopy gets hung inside, and it becomes a temporary theatre space. So this will be reappearing around the city of Manchester in the north of England once it's possible to do that kind of thing again. This is a project, unfortunately, not going to be realised, but a project for London Zoo with Foster's and Expedition, the engineers. So on this one, we were involved in a pre-tender advisory service early on, basically studying the potential, in this case, of bamboo, laminated bamboo, in forming these freeform shapes and prototyping those, and kind of studying in fair bit of detail what the manufacturing route would be for these things. Some more conventional, CLT and glulam building. I think Fabian's going to talk a lot more about the relationship to BIM and how we, as an industry, are sort of needing to be very, rigorous in how we describe our buildings precisely and early in how they get integrated with their manufacturing processes. On this one, we had an appointment at stage 4, REBA stage 4, so pre-tender, but we took on the detailed design of the timber frame, built a CAD work model, so a full 3D model that would be basically immediately able to go into fabrication, down to the level of the, every bolt, every screw modeled. So I think there's I guess an emergence of that kind of attitude where a timber specialist designer gets involved early to really to preempt the manufacture of the building. Project that's on site in Oxford, Burial Sports Pavilion with Niall McLaughlin. This is just an install job for us, but kind of fun. It's a nice stacking of all of these chestnut beams to make a roof. These were just taken yesterday, these photos. Project just sort of between design and making at the moment. This was developed with a community group for a place called Westonbirt. It's like the National Arboretum in the UK. So kind of playing with material from the site, it's going to be constructed from oak laths on the site, thinking through a strategy that would enable a community engaged build of this project. I'll talk about this one a little bit more. So this is, again, it's currently in the workshop in Bristol, little glazed grid shell project in laminated oak. I'll talk a bit, I'll talk through the workflow on this because I guess it's an example of sort of allowing the manufacturing strategy to inform the geometric form finding, a kind of iteration between those two or interaction. So it's going to be a little glazed kind of courtyard roof. So there's a defined boundary for the piece, a sort of twisted four-sided shape. So there's a first step of doing a inverted hanging chain type form finding, a mesh form found into an optimized compression shape, and then mapping a continuous surface on that. And then I guess this was a key move. So the lath pieces are following geodesic lines across that surface. So these are the short path lines from edge to edge, which have this geometric property that you can follow them with a ribbon of material. So a plank of wood can follow those lines just by bending in the easy direction, in the thin direction, and by twisting. There's no need to do any bending in the sort of fat direction. So they're not singly curved, and they do take up a full kind of three-dimensional shape, but they're makeable from straight planks of wood just by twisting them and bending them. So there's a mapping of those shapes, a fair bit of sort of optimizing and playing, getting to meet the corners, think about how they meet the edge beam, and then that's those laths pipes, volumed out. So obviously a layer above, a layer below the initial grid there. And then there's going to be some mushrooms that hold off the glazing, all happening at the moment. So basically each one of those laths shapes was mapped out, and then sort of sections along it, the profiles taken into into a plywood jig, which allowed, as I was describing, straight, I think they're 15 mil thick laths of oak, so straight pieces to be glued up. You can just about make out the twist, I think, possibly in that one. Not hugely twisted, but it's enough to take up the curvature over the surface. This is it coming together. Very satisfying when everything fits, obviously, and something very beautiful about the quality of the oak. So that was that one. So that was a flavour of what Xylotek's up to, the company. I'm going to sort of jump back in my history a little bit to some of the academic work and some of the stuff we've done with the AA. So initially it was teaching in London. Actually, this is a preemptor to that. So before getting involved with the AA, or maybe just while doing it early on, I was working in Arup in the Advanced Geometry Unit. We were involved in the sequence of the Serpentine pavilions. So this was the Caesar one in 2005. And sort of by chance, I kind of landed on this, was a structural engineer, but also ended up writing a script that defined the robotic geometry that all of the, I think it's 427 pieces were defined by, and then they were cut by what was then Finforce Merck, now Zublin. in Germany on the robotic arm. So kind of, you know, an early piece of robotic fabrication, you know, all different, making this lamella structure. That led into a series of pavilions with students at the AA, kind of taking a similar premise in a way, sort of summer event pavilion, sponsored by Finforest, and kind of exploiting the maximum of what we could do with a three-axis CNC machine. So no kind of freeform cutting, just cutting sheet, you know, working with students to produce these things. That fed into then my taking on a job at a place called Hooke Park. So it's in Dorset in the west of England. The AA inherited this from a furniture school, the Parnham Furniture School, around 2002. Inherited the campus, inherited a forest with a mix of species, a really kind of rich mix of species, which is, you know, has an interesting, I guess, kind of material dimension and also a time dimension. Like each of these stands is growing in at different stages and will be harvested at different times. On the campus, there's 3 buildings from the Parnham era, from the furniture school, including this one by Xylotek, stunning building, the workshop building, made out of spruce spinning, so straight pieces of wood bent elastically into this arching, bit like a grid shelving, an arching form, you know, using the elastic property of the material to form this incredibly stiff shape. And that got used for like the pavilion projects. So that's, you know, one of those things being made in there. You know, I think we realised the absurdity about using finished spruce in a woodland of our own that was surrounded partly by spruce trees. And I guess that prompted a kind of, you know, a series of projects that really revisited some of Xylotek's ideas early on about how we use the immediately local material, you know, the undervalued material of the woodland. So again, I guess it's back to that idea of kind of giving the material some agency in the process, you know, not just taking what the standard product off the shelf is, but thinking about what you have and what you can do with it. So students working with the forester, you know, a lot of the woodland is a beech, beautiful material, you know, planted for a furniture industry that didn't happen, you know, not conventionally used in construction, very amenable to steam bending. The students got very excited about the processes of steam bending. There's something magical. It's a way of manipulating wood to give it geometry, using a kind of plastic deformation rather than a elastic deformation as a means to give form to the wood. And I guess what's clever about it is that the grain continuity of a straight plant gets preserved in the curved shape. So if you compare it to taking a block of wood and carving a shape out of it, you'd be breaking, you know, you'd get a short grain. The grain wouldn't align with a piece of wood. But, you know, through steam bending, you do have that benefit. So students invented, you know, big bending jigs, kind of sort of semi-digitalized process, you know, digital model, which was then projected and kind of mapped onto the bending jig. Lots of strategies of how you allow the pieces to dry and not creep and things like that, and then pre-assembling patches of this structure that then came together in this shelter for the future air drying of timber. So that was that one. There's a few other projects at Hooke Park, more on sort of domestic scale and, you know, kind of shed scale, which you can see on like the Design and Make website has details of lots of those, but I'm just going to pick out a couple of them. So the boiler house was the year after. So I guess having gone to that effort of giving curvature to pieces of wood through the processes of steam bending, there's another kind of realization that actually a lot of the trees at Hooke Park had these basal sweeps. You know, they'd grown on a slope. Initially, they'd sort of headed out through the fern to find light, you know, gone the wrong way, realized where the sky actually was and changed direction and formed these curved pieces of wood. You know, to a forester, they have zero value or possibly negative value, because how do you extract those? You know, you can't drag them through the wood. You can't stick them on a lorry to go and get pulped. You know, they're a real problem for a forester. But I guess to an architect, you know, there's, you know, even just in this simply curved piece of wood, there's potential there to do something with it. You know, so very simple kind of, you know, Xbox Connect scanners. You know, nothing high tech particularly, and then the 3D scan form brought into a design workflow, various scripts and kind of processes to compose a form from the whole set of these curved pieces of wood. I mean, not the cleverest use of wood, kind of taking a sort of log cabin sort of stacking idea, not using it sort of cleverly in any structural way. But I guess that kind of pushed the ambition into the next year, the woodchip barn. So this is the last project I'll talk about in any depth. Just kind of work through the story of this project. So I suppose the ingredients in the thinking were, okay, having done that project with the curved wood, so identifying that a lot of the trees at Hooke Park had grown with forked components. So a beech tree typically grows and splits. You know, you have these sort of components within it. So there is an opportunity to use that. There's a great precedent in shipbuilding in France and in England it's particularly the 17th century, you know, forests being grown and nurtured deliberately to make non-straight timber, you know, the opposite of what foresters do today, deliberately growing in potential geometries for components for warships, you know, the Tudor warships in the UK, you know, and a huge kind of industry and skill set around mapping and sort of surveying for where those components might exist in a tree. I guess the other ingredient that was sort of becoming available at Hooke Park was the 6-axis robot, you know, the generic industrial robot that kind of gives you the ability to work so flexibly and 3-dimensionally with a piece of wood, even if it has no kind of conventional sort of orientation or sort of standard form. So there's a fork coming out of the woodland. There's the robot arm starting to do things. So there's an exercise in initially 2D photographing as a kind of crude scanning exercise to get a catalogue of standing geometries, and then sort of in parallel with working through the kind of structural geometry and a you know, sort of engineering drive, identifying which of those would be useful in a structure. So these are going to become, I showed you that image at the beginning of the talk, that standing tree fork truss. So these are going to become components in that. So 3D scanning them, obviously another very valuable technology that's become, you know, very, very accessible, and allows particularly this kind of strategy to be deployed. So you can scan and extract the natural form very easily and bring it into the digital realm very easily. Those 3 red dots are pretty significant because they relate to the some reference points drilled in the wood that allowed the positioning of the wood, you know, of that fork to be kept consistent both in the digital and in the physical, you know, in the robot cell in those different realms. So after a lot of effort, Zach Malika, now a colleague at Hooke Park, as a student, really pushed a strategy of sort of optimizing genetic algorithm kind of optimization of where you place the forks to achieve the structural need. And actually quite a simple conversion of that to the machining toolpaths. So the pieces of wood just kind of butting along the compression sort of axes of the truss. You know, so machining these flat faces in the ends of the pieces of wood where they bear on the neighbouring piece, adding some holes as kind of pilots for the bolts that would go through and the shear plates and things like that. And this was a tenon of the connection where the branched tip would meet the top chord of the truss. There you're seeing it being assembled, so kind of mapping out on the floor of the positioning of the pieces, again using those reference holes, you know, a mix of sort of delicate positioning and digital precision alongside very big sledgehammers and, you know, physical forcing to get this structure together, but basically making this truss in the 2 halves. After the forks, this is it coming together on site. So one day of lifting the sort of the sub parts of the truss together, and a few days later the truss standing there. So, you know, you can see around it the beech woodland out of which those pieces came. You know, you could see potential pieces even that, you know, could have been in the structure. You know, I think there's something very profound about being able to make, you know, a large span structure. Okay, quite a lot of sort of digital effort, but actually relatively little machining effort. You know, we haven't sent bits of wood across the continent. You know, we haven't moved Latvian spruce to an Austrian factory to a German, you know, fabricator to a, you know, to an English contractor. Like it's all happened within a couple of 100 meters. So that's that image again of it standing. That's it with its roof on. So it's a home. It's basically a bulk store for the wood chip for the biomass boiler at Hooke Park. Going to wrap up in a second. I think maybe I just sort of stated this, I suppose, in my describing the piece of wood traveling around Europe. But I think just to kind of state it again, like we work in the 21st century where we can kind of work in a in a non-standard way. We have the digital capacity to handle variation, but at the moment our mainstream industrial timber process basically takes a non-standard material, timber, with varying degrees of variation, puts a lot of effort into standardizing it, regularizing it into some form of kind of cuboid shape, gluing it together, and then potentially quite a lot of effort into cutting it back into something non-standard. So I guess it's a prompt. I mean, obviously it's that project's an extreme. It's not going to be replicated often, but a kind of prompt to think a bit differently about how we use our trees. How we can take a non-standard material and use it directly in non-standard components. I guess that reflects back on one of the earlier sort of hints about the future of forestry. There's a lot of impetus to add diversity. I think if you talk about ambitions to plant more trees, if you think about it not from the perspective of the timber industry, but from kind of broader society, that urge is to have more diversity, not less. For amenity value, for resilience against climate change, resilience against disease and fire. A diverse forest and its ecology is a much richer asset, than a monoculture industrial, spruce woodland. So I think there's something to kind of marry, I guess, in the expectations or the needs of the construction industry and the needs of forestry, more broadly. And we'll end actually with just a recent graduate student's image. Seb Birch did a nice project where he was looking at using the crown timbers of the beech, in this case, the top bits of the tree. It really would be maybe firewood or just junk, but making closely packed, dense packed blocks, construction blocks out of that material. Another little speculation. Okay, I'm going to end there. Thank you. Thanks again, Philip, for the invitation. It's a real pleasure to be part of Digital Futures. Looking forward to the conversation.
Thanks. Thank you. Thank you so much for Martin. So we have more than 5,500 audience on Bilibili. I don't know how many on YouTube, but I think it's a great event. You make a very special lecture, especially from non-standard material to non-standard product. So that's a very special, influential practice, actually, which influence a lot of research including. We can see in the States, University of Princeton, they have a special team working on the similar things. And also in the Northern Europe, a lot of universities also make a very similar research. I think it's a very special topic. Maybe after the lecture from Fabian, we can make a discussion together. So as to Fabian, I met you several years ago, 2018 in Zurich in Robot Art. And Fabian invited me or introduced me to visit the biggest factory in Switzerland. I think it's a great experience to me to see not only the Fabian's work, but also how the Zurich people they set up the timber industry, and great practice from Fabian's design to production office. So let's invite Fabian. Would you please make the lecture?
Loving to. Thank you very much for the introduction. So I hope you can see the screen now. So thank you very much, Philip, for the introduction and the invitation to this event. I really enjoyed Martin's presentation. I'm going into probably a bit of a different direction there. So I guess there will be some room between us for discussion afterwards, which I looking forward to. I titled the presentation BIM to Fabrication because I think we need to start rethinking planning and production processes for prefab timber, and I'll try to explain that. But first, let me introduce design to production as such a little bit. This company actually was founded in 2007, but as you already mentioned, started as a research group within the Technical University here in Zurich in about 2005. The idea behind that actually is that we're doing neither design nor production. So it's all in the name, but just in the middle, we're only doing the two, trying to translate from digital design into digital production. And to do that, also in the other direction, try to inform design about production and its capabilities. Because in 2005, we fooled around a bit with CNC manufacturing equipment in Switzerland and quickly realized that the sort of promises of the industry, yeah, you just build a digital model, then you put it on a USB stick, carry it over to the workshop, plug it into the robot, and then a day later you get all the pieces, is not as easy, which probably everyone knows who ever has tried to build a digital model on a 3D printer. Now scaled it up a couple of times, and you know what it's about in real size. So this is sort of the founding core idea behind the company. We claim that we talk both design and production, so we can understand both sides and more or less simultaneously translate between the two. And we put those ideas on the basis of digital data. So we're trying to find digital representations, both of design and production, and translate between the two. That is the core of the company as such. What we're doing is our main sort of service still is we're doing the planning work. So we take over the design that's there, very often working for the fabricator at the very end of the project, trying to do a little bit of design optimization if that's still possible, mainly doing parametric modeling of rather complex designs, and turning that right into fabrication data. So we're going all the way down to digital fabrication equipment. We deliver, if necessary, we deliver 5-axis ISO G-code right to the controller of the CNC machine. Typically, we step out a little bit before that because then we are not called at 2 o'clock in the morning when some milling bit breaks and has to be replaced and all the milling paths need to be recalculated. But actually, the aim is to go as far as possible in this digital chain, if you like, all the way down to the fabrication equipment. For this, we are actually programming our own software, have been programming our own software on top of well-known standard digital planning applications and then CAD programs and BIM programs, as you like. But we recently also started actually selling this software to clients, or at least parts of that. So we are actually providing planning to specialized planning tools, CAD/CAM plugins, even down to web and DB database applications to clients. And on the other hand, we're always trying to get earlier into the projects, as every consultant is always trying to do, because we think there's really some benefits that are coming out of that. And this is increasingly also getting sort of better and better, if you like. So we are offering consulting services for BIM and design for manufacture and assembly, especially for timber construction, but also for other materials and digital fabrication. This is sort of the wrap up of design to production as a company, if you like. Over the past 15 years, we've been involved in quite a few projects. This is sort of a small excerpt from the overall range. As you see, most of them are pretty curvy and crazy. That's for a reason. 100% of them are digital, so there is no project without any digital fabrication in there. All of them are prefabrication. So typically what we do is we prefab components offsite, either already pre-assemble them into larger elements offsite and bring them to site, or then assemble them on site because we think that's a good idea. 80% of them are in timber, which is sort of an accident. That was never really intended in the first place. In the beginning, we thought, okay, there's a gap between digital design and digital fabrication. How can we bridge this gap, independent and agnostic of the material as such? But we pretty quickly learned that timber is actually way ahead of all the other materials in terms of digitalization. And 99% of them are freeform. We are slowly starting into the realm of the right angle now since 2 or 3 years. The background behind that is 100% digital means there's all parametric planning in there. So we're not drawing things, we're actually programming things, sometimes with little spaghetti code parametrics in Grasshopper, like you can see on the left-hand side, more often in more hard-coded things, to come up with rather complex models of detailed projects going straight into fabrication. And we translate that into fabrication data, and we think that we should put as much complexity away from the construction site and into the parts. So this is why they're coming fully detailed. We take a great sort of pains into designing smart details to be quicker on site, because there, as you can see on the right-hand side, it's cold and windy and it's raining and you don't want to be there. It's much nicer in a warm workshop looking at the machine doing their thing there. So what we're trying to do, and this is the project that you've seen in the 2 previous slides, is we're trying to cut a few corners and be more productive with the tools that are at hand in the 21st century. This, by the way, is Eddie, a skier that stood right next to the main stage of the St. Moritz skiing World Championship in 2017, a 19-meter high timber sculpture that we built together with a few companies in and around Zurich and the Engadine down there. So the main idea is really to advance industry that's already there with coming up with new ideas of how to do things in the end. The question already popped up, why are we doing 80% timber? As I said, this is an accident. It was never intended, but it quickly turned out that timber is digital already, so we can use available equipment that's already there. And in most of the bigger carpentries, there's at least one digitally controlled CNC machine. Typically, what they're doing with that is they're trying to be more productive in their standard work, but they're especially around our office here in Zurich. There are a few companies who always try to push the boundaries with the equipment that they had at hand. So this is what comes out of that. This is one of the beams of the Centre Pompidou being 5-axis milled at Holzbau Ammann in the Black Forest in Germany. Timber has always been prefabrication. For a couple of 100 years, carpenters have basically added all the detailing to their parts on the ground and then hoisted things up into the roof because it's much easier, cheaper, and safer. And this is why there's a mode of thinking already there that allows us now to have people that we're talking to that already think in the right sort of paths. And try to actually do more prefabrication than any other trade that we know on in the building industry, even more than on the steel fabrication side. And timber is actually coming around the bend very nicely. So we can do this funky freeform project, like here the golf club of Shigeru Ban in South Korea in Jeju with Bluma Lehmann, because the material properties of timber allow to make curvy things rather easily, as Martin already explained rather nicely. Thank you very much for that. And B, exploit the material properties then to get it very precisely into shape by subtractive milling and CNC manufacturing there, which is great for prefabrication because, as you can imagine, tolerances are always a big issue when you basically build big construction kits, ship them around half the world, and want to build them on site there. So this probably also answers the question why we are only building those crazy projects, or mainly all those crazy curvy things there. Actually, there's two answers to that. The first answer is because we can, because it's actually great fun. It's always a challenge, and you never do the same thing again. And you always have to scratch your head in the beginning and then have a good idea and then come sort of to the conclusion in the end and push the boundaries a little bit more. And then the next time Shigeru Ban comes along and comes with an even more complex structure that you need to realize in one way or the other. And it's always great to do this as a team with engineers, timber fabricators around the table and try to find new solutions for even more complex problems there. So there's a great satisfaction, of course, in that. The other big reason for doing all those crazy, curvy, freeform, Formula One, Rolls-Royce, whatever you call them, projects, is because actually freeform is the low-hanging fruit for us. Freeform projects are the low-hanging fruit because in standard projects, whenever you try to change something and try to especially change the process behind that, someone comes along and tells you, oh, it's been done like that for the last couple of 100 years, and why change anything? So when the aim is actually sort of igniting a digital revolution in the AEC industry, and this is the actual aim and objective that we're following, it's always easier to start with those crazy projects because everybody is already on the tip of their toes from the beginning, and you have much less fights in terms of, there's a standard process, let's just do it like the last time. So we did this for a reason, because we want to actually look into digital futures in the building industry and say, hey, we're all talking about BIM, building information modeling, having digital planning tools in the beginning, doing virtual design and construction, build a digital model before we build the actual thing, having digital twins. There's all those keywords that are being thrown at you all the time. And on the other side, we really need to talk about the actual production and fabrication process in the end, because there nothing has changed for the last couple of 100 years. We're doing things on site. We're doing them manually. People are standing in concrete up to their knees. Everything's rough and dirty and exposed to weather and other things. So actually, we think the conundrum of the building industry not having any productivity gains over the past 100 years, as opposed to all the other industries out there, could be changed by actually looking into digital prefabrication. And the problem as of now is you have BIM already in place, but actually BIM is taking a detour and creating 2D drawings as an output. There's hardly ever any digital data being handed over to the other side where the fabrication happens in other means than 2D drawings as of now. The whole industry, all the tools that are there actually create what we've been creating for the past 400 years as architectural documentation, if you like. Yeah. So this is the first thing that needs to be solved. And the other thing is, of course, if you have 2D drawings, you can go into prefab, but actually still things are solved on site mostly. Yeah, this is what we call the SOS principle. And this is why we're stuck in terms of productivity in the building industry, is our guess in the first place. So how can we change that? Let me show you two projects out of the many, many, many that you've seen already. The first one is a non-standard project. And it's this one. It's the Swatch headquarters in Biel, designed by Shigeru Ban. Opened last year after 6 years of planning and building time. We were pretty lucky to be involved in this project rather early on, which turned out to be really good. It's a timber grid shell of about 240 meters length, actually a big question mark lying on its side. It spans over a street on the right-hand side where it has the width of a bit more than 30 meters. It spans over a street and basically rests its head on the other side of the street on the Omega building. So this is all one watchmaking family, basically, if you like. Swatch Omega is one company. Omega is the more standard rectangular, expensive one on the left-hand side, and Swatch is the more sporty, curvy, innovative one on the right-hand side. This timber grid shell is composed of about 4,600 digitally prefabricated glue-lem segments that were fabricated in Switzerland, most of them actually, a few of them also in France and in Germany by Blumer Lehmann, who was the main contractor for the timber grid shell. On the right-hand side, one of the extreme parts that you can see there, which will find its place around one of the 9 balconies of the structure on the left-hand side. That's most of the regular part of the timber grid shell. Altogether about 11,000 square meters that are covered with facade elements that are dropped into those quadrilateral openings. 2,800 of them, of course, all of them are also individual in their geometry, and there's 9 different types with ETFE cushions, with glass, with solid elements, with and without photovoltaics on top of it, and so on. The whole facade altogether is also assembled from about 65,000 prefabricated parts. Most of them were CNC fabricated directly from planning data, and then prefabricated as facade elements offsite in Germany, mainly shipped to site more or less just in time and then hoisted into place. Also included, since this is a fully functional office facade, are about 20 kilometers of pipes and electrical trays, 1,000 heating and cooling panels that you can see on the right-hand side, and also curved sprinkler pipes running through the beams there, as you can see. So quite a bit of installation MEP going on in the structure also. And the challenge, of course, for us was that we had a twofold process in this whole planning process, cut in half by the tender stage. So there was a pre-tender stage where we did digital modeling and analysis on behalf of the client, Swatch, represented by Hayek Engineering, as part of the overall planning team with architect, engineer, timber engineer, facade engineers, and many others, and support them in the detailing, define the interfaces between the trades, and coordinate them in a 3D model. So basically what we did there is model the structure and the facade, as well as at least the axis of all the MEP going crisscrossing through the structure in digital models, to mainly define the interfaces between the trades, so that we can actually hand those models over to the other side and say, dear facade contractor, here is a little volume model for every and all facade elements that you have to produce. We have no idea how you will build them, but as long as you stay within this hull volume, everything's fine. As soon as you want to get out of there and stick your finger out of this digital 3D volume that we give you, there might be the timber guys coming with the chainsaw. So you have to be careful and talk to them before you get outside of your sandbox there, and vice versa, of course. And that proved to be working actually quite well. Nevertheless, we were lucky and were handed over to the other side, and actually had the chance of being the digital planner, not only for the timber structure, but also for the facade elements, the sprinkler pipes, the cooling panels, and some of the interior outfitting. So we were sort of, together with our models, we were thrown over the fence to the other side, and were part of the planning teams for all those contractors on the other side, which then, of course, led to the fact that A, we knew the models pretty well that came from the pre-tender stage, and B, we could just continue doing our parametric magic on detailing those things down. But in the beginning, and this is sort of one of the main lessons learned from the Swatch project, is it was really crucial to get a reference model up and running very early on in the project. So we defined not only the building axis, which is pretty natural for every project, but also the reference surfaces that precisely define the shape of the building down to fabrication tolerances, which are in timber in the vicinity of 0.5 millimeter, actually. And also the beam axis grid. And all those models actually were defined pretty early on in the process and haven't changed since the tender stage. So there was a common digital ground for all the planning that happened in 4 or 5 different companies afterwards on this project. And they all are basically referencing back to those models that clearly define the basic geometry of the overall thing, including, as I already said, including information for coordination, namely hull volumes for the facade elements and also for the installation. This is really what the tender model looked like. So there's actually no detailing in the crossing nodes there, but there's already cutouts for the facade elements in the timber structure. So they clearly had a division line between the two trades and knew how far they could go. And since I go one back, since as you can see in this model, it's really impossible to see all those elements from one perspective in the 3D model. There was actually a second digital model that was flattened out on the ground. We called that the flat grid. It's sort of a topological representation of this whole thing, encoded into a digital model that worked as a digital twin of the digital twin, if you like. So we could do a lot of the coordination on a table with all the planners involved there on this 2D drawing that included all the facade elements already with their naming and numbering system and their types, and the little blue squares here are actually placeholders for where is there a cooling panel and where not. And the same was also done for all the MEP coordination. So we could do this rather conveniently in 2D and then basically mirror it up into the 3D structure again. And one other important thing that really happened very early on is that we agreed with everyone on a common naming and numbering system for the overall structure. So all the facade elements all have a number combined of the 2 beams where they start. In this case, it's 41 cross 40 are the 2 beam numbers, and this is where the facade element is. And to the very end, 6 years later, every little aluminium profile was basically named and numbered after the system. So you could pick it up and actually know pretty quickly where in the overall structure it would belong to. Yeah, this is another view into the MEP coordination model. You see there's no detailing in there. It's basically just the axis of all the water pipes and air pipes and electrical trays in there. But that was really necessary to coordinate about 5,500 cutouts in the timber structure underneath, because we had to sort of, fiddle them into those 4 layers of timber in the right cutout. So otherwise there would be no continuous timber in the nodes anymore and no load bearing capacity of the whole thing. What you can also see here, if you look closely, is a rather sort of special configuration of this lap joint in the timber. That is actually a development that also had to be done specifically for Swatch, because a standard lap joint is a really old detail where you have 2 crossing members and you basically cut half of each away and then they snap together. The problem is you can only engage this connection in one direction, perpendicular to both beam directions. Otherwise, if you come slightly angled or from the side, or you twist one of the members a little bit, then you get stuck during assembly. So the engagement of this node is difficult. Unfortunately, now we have a long beam with 5 or 6 of those crossing nodes on a curved beam. So there is no common assembly direction for all of those, for all those beams. And this is why we designed this sort of skewed lap joint that is slightly opening up, as you can see there, that allows us to define very precisely sort of an assembly cone, as we called it, a range of angles where you can actually put those 2 things together, fine-tuned to the necessities of the timber pieces. In the end, you could have optimized that for every single joint, but it turned out it looked much better to to only have 3 or 4 different opening angles there, and it worked quickly. On the right-hand image, you see the design architect of the office of Shigeru Ban, Taro, wondering how those things are actually working together. But in the end, it all just snapped into place. Of course, and that's pretty normal for our projects, none of that was done manually, but there was a fully parametric detailing for all those 75,000 individual parts in the facade and in the timber structure. This is actually a rendering out of the detailed fabrication model. You can see the level of detailing there quite well. This is what the fabrication models looked like. So we had, for every part, we had a digital twin in the model that was also going through an approval process to the engineer and to the fabricator, including all the screws and bolts and fasteners that were needed in there. This is, as we call it, the freak show of the craziest elements you can find in the structure, around the balconies mainly. And on the other hand, we had those facade elements. This is one of the 9 types, the glass element, where we have a curved glass panel on top, which was cold bent onto a timber frame that was also 5-axis milled. This is the red part in the left-hand explosion drawing. On the right-hand, you see one of those frames already assembled in the factory, already detailed with also details that would allow to find the exact position for those curved aluminum profiles and other things there. So there's a lot of sort of product development, if you like, in the detailing there that also allows the people in the workshop to put those pieces together as quick as possible. We're not perfect, so there is mistakes in there, but fortunately very few. So the good thing with parametric modeling is typically either everything's right or everything's wrong. So you only have to look very closely in the first 5 parts, and then all the other following 75,000 are hopefully right also. We had mistakes. We had, out of 75,000 parts, we had about 100 wrong, which actually personally bugs me quite a bit, because at least 2/3 of them are actually going back to mistakes I personally made in the programming of the detailing. But the overall rate is, I think, still pretty satisfactory. So 1.5 per mil error rate is allowed even at design to production. Yeah, just to give you an impression, this is sort of the finished thing, an interior view on behalf of Swatch, and I hope I mentioned all the involved people in the team already. The design architect, as mentioned, was Shigeru Ban. There was a local architect from Switzerland, Itten Brechbühl, who did basically the whole on-site work. Leicht did the facade engineering, SJB the timber engineer, and Grune the MEP. And on the contractor side, there was Blumer Lehmann for the timber structure, Roschmann for the facade, Oeschger for those 9,000 curved sprinkler pipe segments, KST for the cooling panels, and a lot of interior work for Dunik and Rüttelsberger. That was also following the curvy thing. So that was the first of the 2 projects. The second one, I'll be a bit quicker in there, is sort of on the opposite end of what we're doing. It's completely rectangular. It's called the Crocodile. It's in Winterthur, which is close by Zurich. It's called the Crocodile because it's actually an old factory area close by Zurich, where they built locomotives, and one of the most famous locomotives in Zurich and in Switzerland was called the Crocodile. So all the buildings on site have different locomotive names there. There's an elephant also. We were entering the project on behalf of the timber contractor, which was Implenia Holzbau here from Zurich. It's 250 apartments, roughly on up to 8 stories, completely prefabricated with CLT slabs and elemented walls, fully installed. So they already included windows, ventilation, electro, and what else was needed. You can see sort of an explosion drawing on the right-hand side of the element you see dangling on the crane on the left-hand side. And that was for us and for the general contractor, which also was Implenia. That was sort of a pilot project in doing BIM to fabrication. So the idea was to have a BIM planning process starting early on, and then being able to come up with also the same way of taking a digital model and doing the detailing down to fabrication level as automatically as possible. So in this case, we were sort of only working on the post-tender side of things. There was a standard BIM process at the beginning by the client and general contractor, the architect and the timber engineers. The handover were IFC models and catalogs of components and details. And we on the post-tender side did the 3D fabrication planning and production data for the whole timber structure, including wall slabs, columns, beams, everything you need there, and the steel parts. The idea was to basically set up this process, feeding it with models and catalogs in the beginning, doing a two-stage verification process with a coordination model and a detail model, and the parametric detailing in between, and then hand out production models in the CAD work format, which is a well-known timber software format, over to fabrication that they could use to prefabricate all the sort of interior parts of the elements, and also create 2D drawings and production data for CNC manufacturing. So this is a look into the model. There's the sort of detailed Rhino 3D model on the left-hand side and the fabrication model in CAD work on the right-hand side. This is 5 stories out of 8 stories in 1 out of 8 building sectors that we planned. So you can imagine what the whole model looks like. And then after CNC manufacturing all those straight parts and panels, there was a manual assembly process at Implenia Holzbau, putting those things together. And if you look at the right-hand side, you see the level of complexity in the detailing that was there, which actually is coming pretty close to what we experienced in the Swatch project, or even worse, because it proved to be much less systematic than we had done it in the non-standard project in Biel. We had a few challenges. One was the detail handling for the BIM model. So in the end, we didn't have one BIM model and one detail catalog, and they matched, but we had 3 different detail and part catalogs from the engineer and the architect that didn't really fully match up, needed to be consolidated and coordinated in the first place. So it's just one example there that actually should look the same on the left-hand side, which is the catalog, and on the right-hand side, which is a section in the BIM model. There was quite a complexity in the MEP coordination there also. In the beginning, it was sort of agreed that electrical pipes don't have to be planned there because you just pull 2 empty tubes down from every appliance. In the end, it turned out that no one really had thought about in the planning process about how tight that space actually was. And so we ended up modeling all the empty pipes in all the walls there to make sure that all the appliances actually had a connection to the lower end of the element. And systematic detailing, as I already mentioned, is also an issue there. If you have a planning team, especially an architect who's not used to doing timber projects, it might very well happen that you end up with 92 different window details for 250 apartments, which of course is a nightmare for parametric modeling, because you have to automate 92 different window details instead of just having 6 or 7, like in the Swatch project. Adds a lot of complexity, adds a lot of work, and also adds a lot of possibilities for errors in there, which you don't want to have in the end. So to wrap it up, the project was designed by Kilger Pop Architects and Baumberger Stegmaier here in Switzerland. The timber engineer was TimberTech. MEP and general contractor both were Implenia, which is a rather big building firm contractor here in Switzerland, and they actually tried to vertically integrate all the way down to the timber contractor, which is also belonging to Implenia. But you have to be very careful if someone talks about vertical integration, if that's just companies that were sort of put together and not really integrated. You basically have the same interfaces in between one big company than you would have outside there in the market. So they have to practice a few projects before they're actually really vertically integrated there. So lessons learned. Are we going square? Now we're having, we've been doing those curvy things for 15 years. Are we only doing square things from now on? Probably not, but we're doing a lot more square things from now on, I think, because we think that timber really is in the pole position now. The digital prefabrication is already there. It is a sustainable material, which will become a much more important issue, as Martin already pointed out. Basically, we're all looking forward at having some drastic pricing for CO2 in the near future, and then concrete will be used for the basement and nothing more anymore, hopefully. And we think that digital mass customized lean and offsite prefabrication could turn building into an actual industry, because as of now, it's mainly craftsmanship. And there's hardly any really industrial processes going on out there in what's called the building industry, where you have enough repetition, where you have enough quality management, where you have enough process management out there to actually realize what's happening. And I think that the turn for going into more industrialized lean offsite prefabrication is really something that could be a turn for the productivity in the building industry there. And also there, I think timber is already in the pole position. As you can see here, this is on the right-hand side is an image out of the module fabrication line of Blume Lehmann here in Zurich also. A lot of school buildings, temporary school buildings, are made from those modules here in Switzerland. My kids are actually going to one of them. The problem that we're facing is that BIM does not deliver the information needed. This is a diagram that I snatched out of Bormann's BIM book from 2015, showing the increase of project knowledge from the design until the operation stage in black, and then red, that's the amount of digital information available in the process typically. And we all know this. Yeah, you basically build up nice models in the design stage, and then you throw away 80% of it and start rebuilding it in the tender stage, and then you throw it all away. You hand over a few 2D drawings to the execution. And then on the other side, in this case, the timber contractors start building up their own 3D models again from scratch almost, to basically use them for fabrication, throwing away most of it afterwards and handing over whatever digital information is needing for facility management in the end. And some of it, of course, is absolutely right, because there will always be a lot more information for trying out things, having alternatives, analyzing things in the stage. But from our experience, all those red curves are basically going almost down to zero after every stage. And that means we have too much information at the end of every stage and too little quality. Yeah? And our take on this is that a lot of this is explainable by having a very unclear objective. So we're basically building shotgun models, aiming into the forest and trying to hit a tree or a pig or whatever is running around there. We're creating lots and lots and lots of information because we don't know what's actually needed on the other side. And this is something that we really need to change, because what I'm trying to tell my guys here in the office is only a small model is a good model. You have to throw away information, and interestingly, it's very cheap to amass a lot of information. Storage doesn't cost anything. Yeah, just throwing anything that you know into a BIM model is fine, because it actually is really cheap. What's really expensive is throwing away 90% of it, and finding the right 90% to throw away. Yeah, that's the actual work that takes a lot of money. Just a side note, I'm not blaming IFC. Yeah, this is not a format problem; it's a content problem. IFC is really just a thing to carry data from left to right, but it's about the content inside the box there. So what we think we need to look into is the current IEC actually mainly neglects design for manufacture and assembly, while prefabrication is all about product development. If you want to have big elements that come onto site, snap together there, you have to think about how you do that. And our role models here are, funnily, Swatch, where we built the headquarters for now, basically saving the Swiss watch industry by coming up with the idea of integrating half of the parts of an average watch at that time into the plastic casing of the watch there. So basically reducing the amount of parts that need to be put together by integrating them into a smart housing. And on the other side, that's something that you all know is a very famous shelf by a Swedish producer that has been manufactured for the past 40 years. Hasn't changed on the outside. It's still 2 meters high, 80 centimeters wide, and 30 centimeters deep. But it has changed tremendously on the inside over those 40 years. All those details that you see there have basically developed over 40 years because I guess the people in Sweden were sick and tired of answering phone calls of frustrated clients all the time who were not able to put this thing together in their living rooms. So what they did is they invested a lot of gray cells into thinking about coming up with smarter details that would allow people less mistakes if they put things together. And this is sort of what we try to do when we say we put complexity into the parts. It's just, hey, come up with details that are self-jigging and basically provide an information already for the guys putting it together, because then they make less mistakes and they save a lot of time on site. So the bottleneck of this whole venture that we're talking about is actually moving upstream. The traditional planning processes do not deliver what's needed for fabrication in the end, because mainly they're still based on traditional models of planning things. And you all know this diagram here, by which basically was hijacked by McLeamy and is now known as the McLeamy curve, but it's actually much older, as Daniel Davis pointed out. Says, hey, we need to put this hump in the effort for designing. We need to move that forward in time, and we need to think earlier about certain things in the process to come up with a proper BIM design process and do a digital twin before we start building. The question that we're posing here is there actually the same thing underneath that? Are we just moving things forward in time, which means we are actually stuck in the same deep shit just 6 months earlier? Or do we need to talk about what's really underneath those two bumps? And that's the discussion where we feel is not enough happening at this moment, where we talk about digital prefabrication out there. This is not same, but earlier. This needs to be completely different underneath there. Or in other words, I still love this quote by Thorsten Dirks, who used to be the CEO of Telefonica here in Germany, who in an interview in 2016 said, when you digitalize a shitty process, what you get is a shitty digitalized process. And we need to get out of current BIM software actually just remodeling shitty processes that we have been adhering to for the past 20, 50, 30, 40, 400 years actually, and think about what we can really do about changing things. We think that time is ripe for digital timber because mass timber is sustainable and digital fabrication is already there. We think there needs to be more industrialized building with more prefab, lean production, mass customization, and a lot more quality management in factory-like environments. And we think BIM and VDC are actually nice ideas, and digital models are already there, but now we have to talk about digital processes mainly, because we want to be right at the center of this and change the building industry for being, more industrialized and more timber in the end. And that's sort of my wrap up. Thank you very much.
Thank you. Thank you so much to Fabian for the great lecture. I think we still have like 20 minutes to make some discussion. So I think some comments already from YouTube and also some questions from Bilibili would be put forward to both of you. So if you like, Martin, would you please firstly answer the question to the audience right now?
Great.
So
is
you're
that
mute? Yeah, please.
Hi there. Sorry, is this the question about the engineering analysis of the components? Yeah. No, it's a really good question. I think the obviously just to sort of recap maybe what I was talking about, but using those kind of found natural forms, or I think the question is also talking about maybe reused forms. So material that I guess doesn't fall into a kind of conventional grading or kind of product categorized kind of, you know, it's not known as like C24 wood because it's just been sort of found in the woodlands. So it does throw up some really challenging questions about how you do prove it from an engineering perspective. I mean, on those projects, we work closely with Arup and a team there led by Francis Archer and his colleagues who were sort of inventive about how we have a different strategy. So quite often it would mean individually testing either individual pieces of wood or assemblies as a sort of means of proving. There's maybe something to expand on, because I think there's a bit of a risk that, you know, timber suffers from being subjected to the conventions of material standardization that, say, the steel industry has, where steel comes off a production line and it varies within a tiny percentage of its performance, whereas wood is a natural material. It does have variation. You know, engineered wood has a sort of is a means of standardizing it, but if you want to have these other kind of strategies, you know, really being smart about how you reuse a material or use the sort of found material, you have to kind of find alternatives to that. You have to have strategies of visual grading the material to hand, or kind of means of like non-destructive testing as you're going along as an alternative to using data from a code book. So yeah, good question. I think there's there's work out there. I think you could probably find that sort of looking at those questions a little bit.
Good. Yeah, I think as to Martin's introduction, the last practice is really interesting about I think it's kind of process followed by the structure performance, this kind of arch form, and then you find this kind of non-standard timbers. You maybe from 3D scanning, you make a lot of different options from different kind of trees. So I'm very interested in the process. Actually, that is because in the nature, all the branches, the degree, all have different kind of angles. So is that a very strong database? And how many different kind of options do you have? And do you have any like machine learning or different kind of methodology to make the selections, the right branches on the right position? Could you briefly introduce all these kind of interesting details in the process?
Yeah, I mean, maybe, is it worth maybe, should I just bring back maybe just one of the images to talk to, because it'll maybe help just perhaps remind people what we were talking about. Just bear with me a second. Yes, so yeah, I suppose the question is around how you kind of reconcile the natural variation range with, I guess, the sort of particular structural needs in that case of that truss. So I guess in this case, there was, I think I described, didn't I, this sort of two-dimensional, where was the image? I've gone the long way. Sorry. A kind of two-dimensional cataloging. So there was whatever there were, I think about possibly about 200 tree forks kind of captured that way. And I guess through that, we did some analysis kind of on the variation there, and kind of cataloging sort of extraction of what the variation was. So understood what the typical branch angle was, the sort of 20 degrees or so that you would typically see. And that kind of iteratively working with the engineer kind of informed the truss geometry which they were going to be made into. So there's quite a lot of, I guess, backwards and forwards, in the process. And then so I guess the structure was designed in a way from this data, kind of in its principles. And then out of these, 25 were selected to be used for the 20 forks that went into the truss. So they went through that process with a much more detailed, full kind of 3D scanning. Now, I think I talked about it very briefly on this slide, and I think there's a whole presentation that kind of explains maybe what I summarised very quickly, and particularly the work of one of the students, Zach, who did set up a Galapagos solver, which is basically taking each of the, I guess, the kind of medial line geometries of each piece, so the kind of the curved centerline pieces of each element, and the target geometry for the truss, so the chord lines, the kind of ideal structural chord lines on which these bits wanted to be sort of deployed. And then it was a process of basically, in Grasshopper, but sort of tested through scripting, but basically placing each fork, placing 2 points on the 2 key points on the curve, so rolling it down so the top tip of the fork would meet the other kind of chord line, and then shuffling the pieces, so sliding them backwards and forwards, swapping them around. I think it was a series of geometric moves that you could make on each piece that was basically processed within that Galapagos solver. If people know that, it's a genetic algorithm solver that would test multiple variations, select the optimum, find within the sort of the landscape of optimization, find where the peaks are, and sort of target that. And there's some quite nice things. You almost see it here that it happens that the fork has a kind of primary and a secondary piece. So the primary trunk, the thicker bits, has a slight diversion, and then the other branch kind of goes off at a steeper angle, typically like that. 8C05 piece shows it quite nicely. And it sort of happens that the more gentle angle change matched quite well the radius of the general arch curve, and then the sharper branch would fit well for the sort of web element of the truss. And then there was other particular conditions, so getting the pieces to meet in this kind of what we call the crotch area, where the legs kind of met, a particular condition to be solved there. So yeah, quite a lot of subtlety and quite a lot of work to kind of do that. I guess computationally quite involved, but I guess it could be a sort of, you could imagine in the future that being a much more kind of automated, sort of available type of process, which would, in a way, back to the previous question, kind of open up the possibility of using this variant, divergent material, whether it's reclaimed material or, it could be reclaimed steel from a demolished building, same kind of strategies could apply. There is a paper that Zach and I wrote for AAG, the Advancing Architectural Geometry Conference, 2017, I think, which talked about that optimization process in more detail.
Mm-hmm. Good. I think I have one more question. Maybe Neil is coming to asking more questions later. I think that's very interesting. Martin focused on this kind of natural raw position material and try to figure out the possibility to position all this kind of raw material into very precise geometry, and approximately to make a kind of a structure which, from a design perspective, is based on this kind of raw material. I think the quality of this kind of process, you can see, is not everything is predictable. Probably you can find this kind of roughness give a very high quality to the position of this kind of structure. That's very interesting, to have a very strong paradox between the raw material, what is raw material, and high quality. So that's maybe from design perspective, my impression. But at the same time, I want to go to Fabian. I think Fabian gave a very high quality, maybe the best in the world, design to production, doing quite great job, because you're 100% or maybe 99% give this kind of high quality of position to the standard components, which is totally based on the computational design process. I know you have a very strong team, and your team actually program and help the design teams to detail all the process and precisely planning the process and construct everything. So I think from a design perspective, my question would like to go to Fabian. Do you think this kind of the design to production is a very special office? Can give more like a kind of model to the other companies, because design to production is unique because of the high ability in programming, also in your experience on timber structure. So I think you're unique. So sometimes the uniqueness maybe is different. From Martin is kind of design quality, but from fabbing, your strategy is a kind of technology based. So do you think this kind of business model maybe could be have a very strong reference to the future generation, and how this kind of process can engage into the design thinking process, or in the tool set, maybe in the plugin of different kind of platform like Rhino? Because right now, maybe the designers use Rhino, but you need to translate this kind of Rhino files to CAD work. But the designers normally, they don't know how to use CAD work. So maybe that's a very strong threshold, maybe to block the designers away from detailing their works to production. So do you think in the future you would like to set up certain kind of plugin or the toolbox and open it to all the designers, which can help more people easily to make the precise of high quality construction in their projects? So that's maybe the question firstly go to Fabian. What do you think on that?
Well, you're touching a very good point, because I think both Martin and I are having sort of a scalability issue. Scaling this principle of finding the right Y-shaped thing in the woods for a bigger project is probably as difficult as scaling the actual application of knowledge to the process that we're doing. And but in the end, from my perspective, after 15 years, it's much less a technological question than actually a know-how question. This is why we're focusing so much on discussing processes at this time, because the interface between Rhino and CADWork actually is there. Yeah? One important thing is to know what is expected on the other side. So what type of model do you actually need to hand over to a fabrication guy so that he can put it on the machine and then assemble it later? And this is the type of knowledge that needs to be sort of either gained by the people building models, or we need to find ways of actually negotiating the interfaces differently than they are right now. As I said, I think the problem is that we're building shotgun models. We're thinking that it might be a good idea to do this grasshopper model in that way, and then throw it over to the fabricator, and they look at it and say, it's nice, but basically we're starting from scratch. You should have probably called us earlier to learn what we expect from you if we really want to close this link between design and production. And that's what we're doing. And that's partly still a technological question. Mainly, it's a procedural question, and it's also a question about communicating on eye level, understanding each other, actually having an interest in finding out how things are fabricated and put together in the end. And I think one of the main problems that we realize now is that especially prefabrication poses a few extra obstacles in this sort of discussion process that's necessary to come up with, because there needs to be much more discussion about interfaces and tolerances and assembly sequences and detailing. In the end, it's all about putting things together. Architecture is about putting things together, but the current BIM models are never talking about joints. They always talk about components. So how will you ever in a standard BIM model, find out if two things really come together on site. If there's an assembly direction, like in the example with our swatch node, if you can actually put things together, or if they just get stuck during that operation. Simply no way of checking that on a digital model, because in the first place, there's no way of modeling the connection as of now in an IFC model. And that's sort of the whole new discussion that needs to start now about how we actually model things so that we can check things that are important later on in the production and assembly process.
Good. Neil, do you have any question you want to put forward?
Yes. Well, first of all, thank you for these fantastic lectures. It really blew me away. And I was, as a Brit, I found out some things about my own country from Martin. I didn't know that Salisbury Cathedral's steeple looked like that, and I didn't know about the fact that they had been growing trees for the British Navy years ago to go in a certain sort of way. Can I just pick up on that question? I mean, what was interesting about, Martin, you were talking, there were two models actually. One was kind of like, how do you work with the material after it's been grown in terms of steaming and things and trying to get it to but also while it's being grown. And obviously that model is kind of, given our time frame today, you can't look so many years ahead, but is anyone experimenting in how you could control the growth of timber in that way? Because that is actually kind of interesting in its own sort of way. It kind of, yeah. Well, thank you.
Yes, I think it's the answer. In various ways. I mean, I think there's groups, I think in Stuttgart, there's a biobotanic group who work very closely with, sort of tree growth and kind of integrating it with connection structures and things like that. There's lots of, I mean, there's furniture scale kind of makers. There's a couple in the UK, I think, who are kind of working with that. There's precedents, I guess. I mean, is it David Nash, the sculptor, who kind of trains very beautiful sculptural forms in growing timber? I guess you could project a kind of genetically controlled version of growth as well, where you kind of, you program the 3D printer of the tree to create geometries that you're interested in, and possibly accelerate the growth, maybe as a sort of approach to the time dimension. But yeah, the temporal question is an interesting one, isn't it? I mean, where forestry had that, there's anecdotes of that tradition, aren't there? Like the trees being grown for the Cambridge Hall roof, that were ready 500 years. The forester comes and says, your trees are ready. But I think there's an interesting potential there, isn't there, in how we really understand deeply understand the sort of physiology, is that the right word? The anatomy of the tree and how it grows. I mean, I think, like in a way, the project is a kind of, in the way, the way I'm presenting it is a kind of provocation. I suppose it's not, I think in a way, like, the realities of the industry and the actual solutions that are going to be born are more in the world that Fabian's presenting, I think, because it's, the industrial reality is the reality. But I think just to sort of check in our thinking about, like, are we misapplying a 20th century paradigm slightly? Or are we setting ourselves up with problems about how we, in the future, deal with these pieces of wood? So I don't know. I think there's stuff there to think about anyway. Thanks for the question, Neil.
Thanks. It's amazing, and it's great. Also, I just want to say, is part of the team that launched this, to see so many people watching in China, to get 5,500 whatever people on Bilibili. So, congratulations, Philip, for somehow organising this. It was fantastic. We've got some further questions. Have you got time for those, Philip?
Interesting question to Fabian. Do you see that? How do you envision the future of automated assembly versus combined with human craftsmanship or intelligence required for complex assembly process, which most of the time it is either impossible or nearly impractical to automate? For instance, do you have any statistic or insight about tooling versus labor and human craft time put into the production and assembly of one of the facade elements of the swatch component project you showed? So that's a question to Fabian, please?
Unfortunately, no, I don't have the exact figures. But it's a very interesting question, because we are often confronted with questions on why is there no robots putting things together in pre-assembly there. And the interesting thing is I've hardly ever seen robots in the pre-assembly of, say, wall elements or things there. It's mainly about cutting things up, and then there's manual labor putting them together. And as of now, there's a reason for that, because if you come up with smart detailing, like in the little shelf that I showed, it's actually much easier to have a few craftsmen in the workshop who are experienced in putting things together than programming a robot putting wall elements together. This is also a thing that comes with architecture, because even in a rectangular project like the crocodile I showed, I think none of the 700 wall elements that are in there are actually completely the same. So you always have variation in there, and be it just sockets for electrical or whatever that are different on one wall to the other, even though they are just stacked on top of each other in different stories. Getting this into a parametric model down to an assembly robot is really tricky, as opposed to coming up with smart self-jigging details that just snap together, and having people who know how to read those detailing. They don't have to measure, they don't have to really think, they just have to grab pieces in the right order and put them together, which is not a really, it's not a totally stupid job. You have to be careful. You have to know a few things about that. But then there's some hard work of putting big panels on that and nailing them down with 700 nails on an element. That's perfectly done by a robot then in the end. So it always will be, and for the near future, at least I would expect, it's always a mixture between automation, mechanization, and manual labor in there, because you have to reach a certain flexibility in these architectural processes that is going to be really hard unless AI is not really coming at us in the near future. It's really hard to get that programmed into deterministic little orange robots that need to grab things and put them together. But it's probably going to change gradually over time.
Philip, you're muted.
Okay. Thanks a lot to both Martin and Fabian. These are great lectures. And also thanks for the great answer to the questions. I think it's a great opportunity to introduce both of you to the world. And also thanks for the generous presentation. I think Digital Futures is a platform to educate more people, help them to understand the digital futures in the discipline of architecture and also the big design topic. It's a great thanks to both of you. I hope in the future we can invite you, maybe give more lectures or teaching workshops in Digital Future platform. So thanks a lot for coming. Thank you so much.
Thank you.
It was a pleasure. Thanks for the invitation.
Thank you. Thank you.
Thank you. Bye-bye. Bye-bye. Bye-bye.
Thank you very much.
Bye.